Hey folks, welcome, and welcome out there this afternoon to TNLearn Mathline. It's a Specialized Segments Friday. Thank you for tuning in. I'm your host, Ernie Roberts, for this session of TNLearn Mathline Specialized Segments. And Specialized Segments, you don't get to call in. Sorry about that. You can still send us questions on Facebook, through email. You can go ahead if you've got problems you want us to work for you. Go ahead and send them in. We'll get them on the next show that's live. But today is one of those days where we get to sit back, relax, talk about topics, do a little bit of math, get your pencil, get your paper, maybe get a calculator close by, and let's sit back, relax, and like I said, let's do some math. And let's see what our topic of the day is going to be about. Where are we going today, guys? We're going, and they are coming to us, the parallelograms. They're returning. Here come the parallelograms. Folks, excitement, excitement. Back a little bit of geometry after our first really live week this week of TNLearn Mathline, our second live week, actually. Wow. Does the season start moving this fast? Yes, it does. Yes, it does. Thank you for tuning in this afternoon. Let's take a look at some good old problems and maybe a little bit of review for the parallelogram here. It says, first of all, which quadrilaterals have both pairs of opposite sides parallel? Well, the hint is in the title of the show today, all right? Here come the parallelograms. So the quadrilaterals that have both pairs of opposite sides are called the parallelograms. Now, there are members of that, quote, parallelogram family, I like to call them that will specialize also that have opposite sides parallel. So first of all, in answer to the question, let's see where we're going to go. We are going to go to a different pen that was working 5 minutes ago. All right, let's see here. The green one is always my friend here. Parallelogram, obviously, is what type of quadrilateral? Two pairs of opposite sides parallel. That's definition. That's the definition. Now, within that family of parallelograms, within that family, got it. How about it? Rectangles, they work. The rhombus, they work. And sometimes we call that rhombi for plural, all right? And that's an R, by the way. Some of you are going like, boy, your letters are funky today, Ernie. And then we've got that last one. It's the rhombus and rectangle kind of pulled together. That's a square, all right? Now, those are our parallelogram family members. Now, some of you are going like, Ernie, there are other quadrilaterals out there. Well, there are. There's the trapezoid, and a trapezoid is not a parallelogram because it only has one pair of sides parallel. So trapezoid is not what we want to look for here. And the kite, which has two pairs of consecutive sides parallel, but no opposite sides parallel, okay? So that's where the kite goes differently. It's not a rhombus, so the kite has its own look, sort of like it wants to be a rhombus, but it's just not quite there, all right? So those are the other two types of quadrilaterals, unless you just want to call it quadrilateral, but these are the specifics. They've got to be in the parallelogram family. Yes, they are pretty special, all right? So let's see some problems that are going to help us to refocus on these, all right? Let's take a look at our first problem here we got. Picture of a parallelogram, A, B, C, D. Now remember we named them in order, either going clockwise or perhaps counterclockwise. This time we're going from A to B to C to D. It's moving in a clockwise direction as we name our quadrilaterals. So if we didn't have any of these letters here, we would want to make sure we pick some point to call A and work around it. Now, since we're going to try to make some sense out of this, of course we always try to make sense out of these things, right? It says solve for the angles if, and we've got two ifs here basically. We know that ABD, now, dear friends, remember how do we mark ABD? There it is, 25 right up there. 25, there it is. And then we've also got BCD. C is the vertex on this one. There is our 110 degrees right there, okay? Now, you say, Ernie, what are we going to do with this? Well, what are we going to do with this? We're going to remember we've got some stuff going on in here. First question we ask, this is why this problem came right after it, by the way. First question we asked was parallel lines, right? Which quadrilaterals have opposite sides parallel? Well, parallelogram. That's what this symbol is. So there we go. We have a parallelogram working for us here. So if that's the case, we know that these little guys right here, let's see if I can make them, they are working in a parallel fashion. So with those little ticks there, wow, boy, those shut up really well, didn't they? But that also means we have alternate interior angles developing between those lines. So this little guy down here at D is also 25 degrees, all right? That's 25 degrees. So that would be the measure of, it looks like BDC. So we can go ahead and say the measure of BDC equals 25 degrees. So there's a nice little solving. We're in a triangle. Let's go talk a triangle here, all right? We're going to look at this as being a triangle, and you know what? 25, 110, wow, that gives us what, 135. So what have we got left over? Well, we want to get 70 degrees between these two little guys. So let's put 45 or 35. Which one is it out there, guys? Let's take a look. I believe it's 45. If it's not, I'm sure I'll get calls about it. But remember, parallels, oh my goodness, yes. So we're going to put 2 ticks on that because that means also we have 45 degrees down there in that corner, all right? Back here for ADB. So let's see, our 2 angles at D, we had BDC, we already figured it out. So let's go with measure of angle ADC equaling to 45. And notice the deal is we have a triangle going on here, so yeah, they should add up to 180. So this gives us 70, 110, got 180, looks good. Now up here in the top, same story. We want to figure out what is the measure of angle A since we have not marked it yet, all right? We basically already said BCD. And if you want 3 letters, go ahead and call it. How about it? BAD, a bad angle. How about it? We have 110 degrees because once again, we're looking for 180 degrees in the triangle. Now, some of you are going out there and say, oh, Ernie, you didn't have to go through all that adding. You could have put 110 right up there to begin with because you remember there are what? Opposite angles of a parallelogram are congruent. Opposite angles in a parallelogram are congruent. So we could have moved the 110 degrees right in there to begin with. So the nice thing about our geometry, the nice thing about these numbers, there was more than one way to get there. You've got parallel lines. You've got 180 degrees in a triangle. You know the formulas, the rules, the properties that say opposite angles of a parallelogram are congruent. We have the alternate interiors. Oh my goodness, so many ways we can work through there, all right? So that's the storyline today, all right? That's the storyline today. Parallelogram is rather specialized. Now let's go over here. Did we name some angles? I believe we've added some numbers here. We have the 110, the 25 already in there for ABD, but we did throw in what? Ah, yes, angle C. So we'll say the measure of angle C, BD. That came out there, CBD. Follow the letters C, B, back to D. And that's going to give us 45 degrees. There you go. And I believe that everything else was given to us, right? Angle C. We need to know angle C, I guess. There we go. So angle C, which we can call that BCD. We've already got it. We've already got it. I was just kind of rambling around here. We got 6 angles up there. They're all measured. Now, let's do one more thing. I see 2 more angles that we really haven't mentioned. Y'all see those else out there? Look, look. How about it? Angle ADC. Angle ADC. There we go. AD coming back to C. I got 70 degrees because I've got 45 plus 25. So there's 70 degrees right there. While we're at it, ABC, measure of angle ABC equals 70 degrees. And you're saying, Ernie, they're the same degrees. Well, you know why? Basically, when you look at the big angle at B, there are 3 of them, by the way, but the big one is ABC, and then ADC down here. They're opposite angles of the parallelogram. Yes, once you've got one of them, you've got the other. That's powerful, okay? Opposite angles of a parallelogram are congruent, and that's a sweet, sweet deal that goes on there, all right? So that gives us a little start here, a little bit of work with those. Throw that diagonal in there. By the way, I bet you could tell me something else about the diagonal. It makes what? Congruent triangles, exactly. So let's take a look at our next link in this whole family. Let's see, which members of the parallelogram family have congruent opposite angles? We just covered that, didn't we? Everybody remember? That would be the parallelogram. We just showed that in that last problem. How about it? Do rectangles? Well, they're all right angles, aren't they? So they have to be congruent. All right angles are congruent, so that worked. The rhombus, they're going to work also. In fact, they're specialized because when the diagonals get there, they actually split those angles, bisect them. And then, of course, if it works for the rectangle, it's going to work for the square. So all members of the parallelogram family, that's the rectangle, the rhombus, the square, and, of course, the parallelogram in general, they will have congruent opposite angles. So we're good on that. We're good on that, right? So quick run here, all right? Let's see where we're going. Let's take a look at a parallelogram without the diagonals. You say, well, can we do that? Sure we can. Let's take a look at it. Right, here we go. Oh, nice yellow once again. And I've given you one big angle. We're going to say angle ABC here is worth 40 degrees. Just using our fact that what we know, opposite angles, opposite angles. Now that would be angle B and angle D. They are congruent. And notice I said ABC. I could have just said angle B. There's no confusion. There's not a bunch of angles at B. There's only one. So we could have just called it by the vertex. But I went ahead and chose 3 letters because it kind of gives you a chance to practice. Oh, ABC, there it is. All right. Or it could have been CBA, you know, as we name our angles. But that's 40 degrees. And we also know opposite angles are congruent. So that angle at D is also 40 degrees. Now you say, Ernie, how do we know what to do with A and C? Real easy, isn't it? Because these are running, yes sirree, they're running parallel. So that gives me same side interior angles off this lovely transversal. That transversal CD. And what do you know about same side interior angles? Or consecutive interior angles as we hear them, or consecutive angles of a parallelogram? They're supplementary, aren't they? Because of that parallel line effect. So put it in there. 40 plus what number gives us 180? Everybody got it going out there? Think. At least 140. It is 140 degrees. I wouldn't lie. Y'all tell me that, right? And then we know, oh, opposite angles, once again, A and C. So put a 140 up there. But also consecutive angles. They work to be adding up to 180. 180. Now, how about these little guys over here? They're running parallel also. It's parallelogram. Oh, the magic of a parallelogram. There we go. Double ticking on there. And going up this way, guess what? 140, 40, same story. They add up to 180. These two also, B and C, add up to 180. So again, A and D adding up to 180, supplementary angles. B and C adding up to 180, also supplementary angles. The beauty of your parallelogram, that's why we like the parallelogram as a quadrilateral. We love rectangles, but we really like parallelograms because they behave very, very well. We love those rectangles. We love those squares. You know, rhombi and rhombus situations are seeming to be the least favorite of my students when we deal with these quadrilaterals. I think they're a lot more fun, though. I think they are a lot of fun because there's a lot of really neat, cool stuff that I can get my geek on about, all right, but that work when you're dealing with rhombi, Speaking of a rhombus situation, it does say a rhombi. You know, there are a lot of rhombi. Rhombi is plural, rhombus. So we're going to say rhombus. Let's take a look at our next problem so I don't get too sidetracked here and out way off the subject. It says, if AB equals 6, find the length of each diagonal of this square. Now, I got real excited about rhombus and rhombi. Well, this is a rhombus, but it's also a square, because it has not only all sides congruent. Here we go. We'll go ahead and put tick marks on them. They're all congruent. They're all the same measure. So since I know it's 6 down here, I can put 6 anywhere I want to on any side that I need in this square. Hey, I can say the perimeter. Perimeter is 6 times 4. It's going to be 24. Hey, I can get the area. 6 times 6. Oh my goodness. Just knowing one number allows me to find so many things. So you say, Ernie, is it going to allow us to find that diagonal? You don't even have the diagonal drawn in the picture. Well, let's draw one in there, all right? Because if we draw one, we've got the other length, right? They're going to be the same length. That's what happens with rectangles and squares. So let's take a look. Connect. Let's see if I can connect these pretty well for you guys out there today. Boom, boom, boom. Here we are. Oh, come on down, little boy. Yep. Come on back up there. Yep, there we go. We got it. We made our nice little diagonal going from D to B. Now, why did I just do that? Oh, remember I said something else? We said we have a square. Well, something important? We got right angles. We got them everywhere. We have right angles everywhere, but what's most important to us right here is the fact we have an isosceles. How did I know it's isosceles triangle developing? Because we have 2 congruent sides, okay? We have 2 congruent sides. That means we're definitely isosceles. If we knew a little bit more about this thing, it could be equilateral, but not today. Because in an isosceles right triangle, you're not going to be able to pull out equilaterals. You know why? Because This is 90 degrees, right? Right angles. Hey, that was pretty good. This is 90 degrees, right? Oh, you got it. All right. And let's go back here. These two have to be 90 degrees also when they add together. So that's going to make 45 and 45. So, dear friends, there is no way you can get an equilateral out of an isosceles right. Now, you can get an equilateral out of one type of isosceles. That's if this angle were 60 or either of these angles were 60, because it would force all of them to be 60. But I digress a little bit. This is a square. So don't everybody go, where is he going now? I'm here with you. Now, let's see what we're after. We're after this guy right here. We'll call it X, because I don't know anything else to call it. If I call it D, you're going to think it's a big D there. All right, so we'll call it X. But it's the length of our diagonal. It's the length of our diagonal. Remember I said something about this thing being isosceles right. So you say, Ernie, what does that mean? Get my hand out of the way, you probably can see. We'll put a 6 right there because that helps me. It helps you visualize. And we think right triangles. Here's this good old friend of ours called the Pythagorean Theorem, which says a squared plus b squared equals c squared, right? The sum of the legs squared. So we square the leg of 6. We square the other leg of 6, and we add them together. The sum means we add, and we get the hypotenuse, which in this case is our lovely x here. It gets squared. So let's take a look at it. Let's take a look at it here. We got 6 squared plus 6 squared equaling to x squared. I like it. Do you like it? Because we know what 6 squared equals, right? Everybody knows 6 times 6. Well, if you don't, you're going to learn it right now, aren't you? 36 we have, because we're going to use it twice. 36. Come along again, put 36 right there. And it gives us to, wow, x squared. Now, think about it just a second with me here. 36 plus 36. Just like saying 2 times 36, isn't it? So we're going to say that is 72. And I hope you remember what I just said, 2 times 36. That's going to be important to us in just a second. That is what we get for our x squared. We're interested in x, not x times x or x squared, all right? So what we've got to do, we've got to come back and remove that little squared. And some of you say, oh, well, that's easy, just throw it away, right? Well, we've got to remove it in one specific way. In order to do that, we've got to square root both sides here. So we're going to square root this x squared, which we've got to do to the other side. Basically, it's a property of equality going on there. And you're saying, ooh, what's the root of 72? It's not even, is it? 72 is not a perfect square. So we've got to think a little bit. And I thought enough to say, let's go to the calculator and find out what it is as a decimal. That's where some of you will be. Some of you will, the question will ask on this, it didn't say, did it? But some of you will say, do we want radical form or do we want a decimal, maybe the nearest tenth, nearest hundredth? Well, let's do both. Let's do both. So let's first of all basically take the fact that x, by the way, that's what the square root of x squared is. It's just simply x equals to the root of 72. And that's the square root of 72, all right? So let's go to calculator and figure out what we got here. I'm going to go to the second button, see where I'm pointing. Can I follow my cursor out there in TV land? Good. Oh, it just went red. How about that? You know, I just punched it. And we're going to put, and you've got the symbol for square root. We're going to, by the way, it's on the x squared key. See where the red just popped up right there on the x squared key. And we're going to pop our number that we want in there, 72, and we'll press a nice big enter. And we're ready to solve it. Wow. It looks like it's almost 8.5. It's very close. If we were going to the nearest hundredth, we can say that x is approximately, notice I've got these little approximate look, let's say about, since we bump up on that 5, we'll bump it up to 4.9. Almost 8.5, almost 8 5/10. If we were rounding off the nearest tenth, we'd have it. 8.5. 8.5 would be very, very much accuracy there, all right? Now, that is one option. That is the decimal approximation. So about 8.5. If you were going to take a ruler and measure that out, let's say these were centimeters, that would be about 8.5 centimeters, all right? Let's see where we're going to go otherwise. You said, what about that radical form? That's what I heard you say, right? Yeah, we've got to simplify this root of 72. Now, when we simplify square roots, this is a quick little algebra review moment, all right, to everyone. Let's see what we've got going here. I mentioned earlier that 36 plus 36 would also, same thing as saying 2 times 36. Remember, when we try to simplify, we want to break this 72 down into a perfect square, which 36, by the way, is a perfect square because that's what 6 squared is, times another number. Now, those of you who are very astute, and that's everybody who tunes into Mathline, aren't you? You all are. You're great students. We appreciate you. Great adults who want to find out what's going on also. What I've got going here is I can take the square root of 36, and it's going to be 6. So what I do is I basically work this half of the problem and say pull out a 6, because that's what the square root of 36 is. What have I got left behind? I've got this pesky little root of 2. Now, I've got a feeling some of you are going like, are we done? We are done. That's simplified radical form. All right, that's a radical form and it's simplified. 6 times the square root of 2. Let's see what the calculator tells us that equals. All right, let's go back here to the calculator. We got 6. We're going to say times, I'm just going to put it right in there. We're going to hit that second button, put the square root of 2 right there next to it. Your calculator knows what to do. It says we're going to multiply. And we're going to see if we get the same decimal approximation. Yes, we do. So that tells me that the root of 72 and the 6 roots of 2 right here, they are one and the same. It's just a simplified form to look at your radical without having just, okay, there's the root of 72. And 6 of one, half does the other. No pun intended, of course, there. Now, I know some of you are out there thinking, remember I said something about we have some astute people who are watching? I did not say, I said astute, all right? That's a good word, it's a good word. Some of you are going, what did he just say? I said astute. And now that we've learned a little vocabulary there, what about 9 and 8? If we had spoken and chosen 9 times 8, 9's a perfect square. 9 times 8 gives me 72. And yes, I can make 3 times the square root of 8. You're on your way. You just have not gotten into the simplest form yet. Because 8 inside here will break down once again. We've got a 3 on the outside. On the inside, we can break down 4 and 2 to get our 8. And guess what? Right there is a 2 waiting to multiply. Waiting to multiply, which is going to give us 6, and the root of 2 is still left over. So all 3 of these square root representations all come back to the same thing. 6 roots of 2. They can go back to the root of 72. They go back to 3 roots of 8. If you type that in, you'll get the same value. And what are they actually equal to? If you're looking at a decimal approximation, about 8.5, almost 8.5. So there's your story with the square a little bit. No, it kind of went along round robin for some of you, but I want you to see there's more than one way to come up to possibly that final answer. Let's take a look at one more situation here, a quick quiz type question here. Parallelogram, we've got nx, look where it is, right there, going out to here. And px, it's a parallelogram, folks. Guess what? We know the diagonals bisect each other. We know these 2 parts are equal to each other. They are numbers. They represent numbers. So now what we've got to do is find out what a is and then find out what nx, px, and then, oh my goodness, just double it. You got np, right? So let's do it. So we got 4a, I believe, minus 15 on one side of the going here. And on the other side, we have 2a plus 5. So what we got to do is get the a's by themselves, right? That's what we're looking for. That's what we're working after, all right? So let's work with that. Let's do it. So we're going to subtract 2a off the right-hand side. We're going to subtract the same old 2a off the left-hand side. Well, look where we are. We're at 2a minus a 15 equaling to 5. I like that because I see something coming. Let's add 15 to both sides. Story goes, 2a equals 20. Also says, Ernie, you're out of room at the bottom of the page. So we're going to say a equals 10 because we want to know 2 times something gives us 20. That something is 10. Everybody with me so far? Again, just a quick set them equal to 0 because it's parallelogram. Special guy here, right? Diagonals bisect each other, so they are equal. What I want to know is now what is nx going to equal? So we're going to put in 4 times our 10, go back up here, use this little guy here. 4 times 10 minus 15. While we're at it, let's see what 2a plus 5 is going to give us. Boy, I hope it gives us the same thing because otherwise I'm in trouble, right? Otherwise we're all in trouble. And we're almost at the end of the show. All right, so let's see. I've got 40 minus 15. That gives me 25. It could be 25 feet, it could be 25 inches, whatever. It's the units. Put a 10 over here, 2 times 10. Add 5. Y'all clicking and kicking with me? We've got 20 plus that 5 gives us, 25. They're supposed to be the same, aren't they? So this was, what is it again? This was nx. This was np. The big question is, no, it wasn't np. It's what? It's px. It's xp. All right? The big question I was about to ask is, what is pn or np? It equals 50. Feet, inches, whatever you've got going. There you have it, all right? Quick run today. I hope you've enjoyed your time with Specialized Segments. We will be back again next time looking for you, and it's going to be a live show, I believe, next time, so see you then.